In the 1930s, my grandparents had a new home built for them, and I am curious, but never thought to ask my grandparents nor my parents how they were able to, my grandparents were able to have a new home built at the beginning of the Great Depression. And they did manage to keep it because in the 1970s, I purchased that house from their estate, my grandparents' estate. And one of the first things that I did was I had the walls insulated because the construction method at that time that my grandparents had their home built was not to insulate the walls. So, of course, I did an analysis of the annual consumption of BTUs before the walls were insulated and after the walls were insulated. And you can see that the insulation of the walls retarded the heat loss substantially from what it was before the walls were insulated. So there are some formulas for that that I used, and Q is the total BTU heat loss, which equals U, which is the reciprocal of R, 1 over R being the total insulating value or the resistance to the transfer of heat, the R value, and that's the reciprocal of that times the area times the change in temperature for an hourly heat loss. And TI is the temperature inside, and TO is the temperature outside. The annual heat loss formula that I used was similar. It's the U value times the area times degree days times 24 to get the annual heat loss. And I have a video which I will put in the more section of this video that shows how to calculate degree days. But the purpose of this video is to talk about global warming, not to be a tutorial on how to calculate heat loss. But basically, I use the pool analogy in that if the pool in your backyard lost 100 gallons of water a week and you wanted to keep the level of the water the same throughout that week, then you would have to add 100 gallons of water to keep that level the same. If your home loses 100 BTUs per hour, and you want the temperature inside of your home to stay the same temperature, then you would have to add 100 BTUs per hour in order for the level of the temperature to stay the same inside of the house. You're losing heat through the walls to the outside in the wintertime. And so we need to supplement that loss in much the same way we would need to supplement the loss of water in a pool. And you can see that annually I would need, when I purchased their house from their estate in the 1970s, before I insulated it, I would have to create by burning natural gas or fuel oil, propane, or coal, or some sort of heat source to the amount of 336 million BTUs a year in order to insulate, in order to keep the level of the temperature inside of the house during the winter at the same temperature. Once I insulated it, I only needed to generate 91 million BTUs to keep the level of heat inside of that house at the same all the time. Also, if I were to continue to add the same amount of BTUs to that house annually that was added previously to the house after I had insulated it, you can imagine that that house on the inside would be incredibly warm. In fact, probably hot would be a better temperature definition or description. So it's the same with the pool. If you're losing 100 gallons a week and you add 200 gallons a week back, that your pool is going to have an excess level of water in it, or of course it would overflow. So I took a look at the parts per million of carbon in the atmosphere from the 1500s to the 2020s. And that line is represented, the carbon in the atmosphere is pretty steady all the way across from the 1500s to, in this case, it's looking at about 1940 where we started to get a substantial jump. I think it was 1960s it started to really climb up. And what that was, is that we're adding more carbon to the atmosphere by parts per million. So before the Industrial Revolution, we had a pretty steady line of carbon parts per million in the atmosphere. And now it's starting to rise up in parts per million. So what happens is if we see, look at this cloud level rather as the carbon in the atmosphere, the light from the sun comes to the earth. When it hits the surface of the earth, it changes from light to heat, and that heat is then reflected back out into the universe. But we had a very steady amount of carbon around the atmosphere, around the planet, which bounced some of that heat back and kept it in as insulation. And it kept the temperature of our planet at the level that it was at to sustain life on this planet. And it did that same level of well before the 1500s, but my chart only starts at the 1500s and goes across. And then with the introduction of the Industrial Revolution, where we started to use machines to do the work for us, whereas before we used human beings and animals to do the work for us, we started using machines, and those machines were powered by fossil fuels. And those fossil fuels were burnt and started to add more carbon into the atmosphere. So if we take a look at the illustration here, as we add more parts per million to the atmosphere, we are additionally insulating the planet so that less heat is able to escape. So when I see arguments about global warming and they go back hundreds or thousands of years for their justification that global warming is just weather, I think that we really need to start from the Industrial Revolution and pay attention to what's going on there, because we are super insulating the atmosphere. And when we do that, then we're losing less heat through the through that ring of carbon that for the longest time was the perfect amount of carbon in the atmosphere to allow just the right amount of heat to escape to maintain the particular temperature on the planet. So just like when we insulate our house, we are retarding the escape of heat from our house to the outside in the wintertime. And we're doing the same thing with the carbon that's in the atmosphere. So if someone wants to make a global warming argument against global warming, using the historical data before the Industrial Revolution, as your justification for temperatures rising and lowering, I think that that's a false argument. The argument now is that we are, by burning fossil fuels, we are adding carbon to the atmosphere. And by adding that carbon to the atmosphere, we are increasing the insulation value of that carbon, and we are retarding the escape of the heat from what it was perfectly balanced before the addition of carbon into that atmosphere.